So we know the product rule, we know the quotient rule for the derivatives, but how do we know that these work? The nice thing about derivations, when you have the final solution you're trying to come up with, either the product rule here or the quotient rule here, is you know what you're working towards. So a little bit of basic algebra manipulation would get us from our starting points either in the product of two functions or the quotient of two functions to force it into the derivative forms that we have used. So we'll do this big, relatively quick video, just close out this section. Remember that the product rule says the product of two functions, the derivative of that total function is f prime g plus f g prime, right? So alternating the original function and the derivative. So how do we prove this out? Well, we need to use the basic definition of a derivative, which is the limit of the slope, right? So delta x approaching 0 means we're looking at a smaller and smaller space between 2 points. And so we represent that with a x plus delta x as my further out point, and then x as my earlier point. And we just plug in the functions for each of those, right? So for this final version, we want this to look like the derivative of f prime, or limit delta x approaching 0, fx plus delta x minus fx over delta x times g of x plus f times the limit version of g prime, right? So we're going to start off with the full function, rewriting it in this form, and then building out through algebraic manipulation this final form, and that'll prove out that the product rule is true, right? So starting point, we have the full function, take the derivative of that, so f g prime, that can be rewritten using this definition as fx plus delta x times gx plus delta x. This right here is basically yx plus delta x, because the full function is fx gx. Subtract the yx term, fx gx, over delta x. Okay? And I want to manipulate this so it looks in some form like this. So we can add and subtract the same value to help me break this single fraction into two fractions. Because I know where I want to end up, we choose fx plus delta x times gx, right? So we subtract it and then we add it once. So this cancels itself out. But we can segment this term with this one and this term with this one, and that will help us get to the final two forms, right? Shown in red and green text there, right? So we separate the two. So this one term, and then this secondary term right here, all right? And then I can pull out fx plus delta x in this case here, and I can pull out a gx from this case here. And you can slowly see, right, pulling out the gx term is probably going to give us this component. Pulling out fx plus delta x term may give us some form of this green side here. So I have limit of fx plus delta x times limit of the remaining components, right? Gx plus delta x minus gx. This looks exactly like this term here. Then I have limit gx multiplied by limit fx plus delta x minus fx over delta x. That looks like this term here, right? So the last thing we have to do is to clean up these initial points here and here. Well, limit of delta x approaching 0 for g of x doesn't matter. It's just g of x. Limit of delta x approaching 0 for fx plus delta x, this is the same thing as fx because delta x is approaching 0. So we rewrite that, and this looks basically like this equation, but they're swapped right here. And so that proves out, right? So fx, this is g prime x, that's gx, and that's f prime x. So that's the equivalent to the product rule. So let's take a look at the quotient rule, and we'll do pretty much the same thing to prove out the quotient rule. All right, we're going to do the same thing with the quotient rule. We're going to build out the limit definition of the full derivative, and we'll try to make it look like the derivative of the quotient rule solution, right? So remember, the quotient rule solution says f prime times g minus f g prime over g squared. So we can expand this out in the limit form in a second. So first, we expand the total derivative in the limit form. Remember, it's yx plus delta x minus yx over delta x. So yx plus delta x is plugging in x plus delta x into this term. That's what's shown here, fx plus delta x over gx plus delta x. And then yx would just be this exactly, right? fx over gx. So we got yx plus delta x minus yx over delta x, and we take that to the limit delta x approaching 0. And what we want this to eventually look like is the full form of the quotient rule solution, right? So here we have f prime, so that shows up as limit delta x approaching 0, fx plus delta x minus fx over delta x, and that's just gx, minus fx times the derivative of g prime, so limit delta x approaching 0, gx plus delta x minus gx over delta x, divided by g squared, or gx squared. Right, so we need this to look like this form. To help us do that, we try to get a common denominator. We'll have a gx plus delta x here, I have a gx here. So I can multiply by gx over gx and gx plus delta x over gx plus delta x over here. And that's what's shown here, right? So trying to force this to have a common denominator. So somehow we'll get this common denominator as well. And let's see what else falls out. So we got common denominator gx plus delta x, gx times delta x. That's showing up here. Okay, that's it. But I have two terms, 1, 2. I know when I expand into these two halves of the fraction and the limits, I'm going to need 4 terms essentially. That's kind of what we did for the product rule. So let's see what we can add or subtract in the numerator to help me get something that looks more like this final version here. So I'm going to add and subtract fx gx, right? So I subtract it here, add it here, so there's no change to the equation itself. And then I can segregate the two parts of this fraction, right? This one part and then this another part, and then we can factor out terms. So for these first two terms here, I can pull out a gx term. That's showing up right there. So then what I'm left with is a limit delta x approaching 0 of fx plus delta x minus fx divided by that common denominator. And then what I'm left with on the right side here, I can factor out an fx term right there and there. That's what's showing here. And then what I'm left with is the limit delta x approaching 0, gx minus gx plus delta x. That's what's showing there, divided by the common denominator gx times gx plus delta x times delta x. Okay, so then I can pull out the common denominator from both terms. And so that's what's showing up right there, right? So this is the common denominator, 1 over gx times gx plus delta x. I leave the delta x in the initial limit components because I know that if I do that, I'll get my derivative form here and here. So it's intentional to leave it in. So here I have a limit delta x approaching 0 for gx right there. And there's no delta x term there, so this is just going to be gx. And then I have limit delta x approaching 0, fx plus delta x minus fx over delta x from this term right there. And that's just your f prime term, which we see right here. Plus limit delta x approaching 0, fx, that's this one right there. Again, just like gx, there is no delta x term, so this is just going to go to fx. And then what we're left with here, when I pull out part of that common denominator, is limit delta x approaching 0, gx minus gx plus delta x over delta x. This term is essentially this, but with a sign difference, right? That numerator term is swapped around that negative sign. So there would be minus all of this, which is great because there is a minus sign or a negative sign right here. So 1 over gx, gx plus delta x, taking that to the limit delta x approaching 0, gx plus delta x is just going to be gx. So there's my 1 over gx squared term right there, right? And that shows up in the final solution as well. Right here, this limit gx is just gx, and this is my derivative f prime. Then I have minus, like we said earlier, because of this switch here. So this will give me my g prime. And limit delta x approaching 0, fx is just fx. So if we clean that up a little bit and use a common denominator, now this looks exactly like this form. I guess I have gx f prime swapped in this first term, and the second term looks exactly the same as what we had there. All right, so quick proof of the product and quotient rule. Now we can use it confidently and apply it to a lot of these different trig and exponential, natural log, x to the n power type trig or derivative terms. So now we're going to look at some applications when these basic derivatives show up in physical systems.